Good evening, everyone. I think almost 55 participants are here. So I think we can start the proceedings. So I would like to welcome everyone on behalf of Chemical Engineering Sectional Committee. So I'm Shanaka Mahavatta. So this is the first knowledge sharing session program we are arranging from the Sectional Committee, Chemical Engineering. So today we have our guest lecturer, Dr. Anushka Pereira. He is an alumni of University of Moratuwa, Department of Chemical and Process Engineering. Dr. Anushka is graduated in 2007 from University of Moratuwa, and then he has completed his master's and PhD from University of Southeastern Norway. And then currently he is working in capacity as a senior automation engineer in reputed industry solutions provider in Norway. And he has a lot of experience in designing control systems and automated systems. And he has working experience in designing all these things. So he will share his knowledge about industry and experience which he has gained so far during his learning and working experience. So I would like to invite Dr. Anushka Pereira to start our lecture on control systems for small and medium scale industries. Dr. Anushka, please start.
You all hear me?
Yeah, we can hear you, Anushka.
Yes, okay.
Yes.
I hope you all can see the presentation now.
Yes, Anushka, you can proceed.
Yes, yeah, okay. Okay, welcome to my presentation on control system design techniques for small and medium scale systems or small and medium scale processors. Today we will discuss several topics related to controller design and implementation. As I mentioned before, we will only focus small and medium scale systems, which is something a small group of engineers can handle. Let's say a group of 10 engineers, including let's say one software developer, someone who can work with electronics. It is not necessary that that person has a degree in electronics, but if I mean a bachelor's degree in electronics, but if it is the case, that's ideal. And also someone with the background in mechanical engineering and someone with the background in chemical engineering and so on. Mahavatta already explained, already gave a simple brief introduction to my background. I have a mixed education, a bachelor's degree in chemical and process engineering, and after that I started to focus more and more in systems and control engineering. My educational and work experience is related to mathematical modeling, process control, software development, scientific computing, and so on. The targeted audience, anyone who interested in the following areas. I'm pretty sure that anyone interested in system and control engineering and or software development and or embedded systems, then probably will have something to take home from this presentation. Since I am a chemical engineer, I would be a little biased to chemical engineers, but of course others can enjoy. I hope others would enjoy the presentation as well. The agenda. First, we will briefly talk about modeling and control of physical systems, and how to implement a simple control system. Then we will discuss how to implement simple a class of simple control systems using Raspberry Pi computers and Python. Then we will go a little further and do something a bit more complicated and interesting. We will talk about how to use microcontrollers for we'll consider how to use microcontrollers. How to use microcontrollers for small-scale automation, to solve small-scale automation problems. And finally, we will discuss something a little bigger than microcontrollers, an architecture which is based on real-time Linux, which can be used to automate a class of medium-scale systems. So let's start with modeling and control of physical systems. I hope, or I assume that most of you have heard about these terms before, but I will provide a brief introduction to these concepts. So let us consider one or two examples. So example one is about a chemical reactor with a heat exchanger. And if you haven't, if you are not familiar with chemical reactors, just think about something similar that you are familiar with. In this reactor, you can see that there's a one input stream coming in, liquid stream coming in, and one liquid stream going out from the system. So, so the objective is let's say the objective is to maintain the temperature inside this reactor at the desired value. Let's say 5 degrees Celsius over the ambient temperature. So then we would need some kind of heating element. So let us assume that we would use a flow of steam to provide the heating. And to regulate the amount of heat supplied to the system, we can have a gas. We can have a valve which can be used to control the amount of steam flow go through this valve. If you want to regulate the temperature of this, regulate the temperature, we need a sensor to measure that. So that's the very first thing we should do. We should place a sensor, and that would measure the temperature. And as I said before, we need a valve to regulate the gas flow or the steam flow. There are several ways of controlling the temperature. The easiest, not the easiest, but one possible ways is to manually regulate the temperature, meaning that someone continuously monitor, well, may not be continuously, let's say every other 30 minutes. Manually, that person would monitor the temperature and accordingly manually change the valve position. Well, it is obvious that it is not the ideal way of doing that, because it is not practical. One person would be standing closer to the system and day and night and do the job. So we need some kind of a standalone controller which does it for us. So the controller will read the temperature, and if the actual temperature is lower than the desired temperature, then probably it will open the valve and consequently you will get more heat delivered to the system, and hence the temperature will go up. And we can do the opposite if temperature is greater than what is desired. So a couple of things about measuring physical quantities like temperature, pressure, and so on. There are many ways of reading a sensor. For example, in this case, I have assumed that the sensor provides a current signal, a 4 to 20 milliampere current signal. Then we have to convert that signal to the corresponding process value. In this case, it is the temperature. But let's say that you have a data acquisition device that cannot handle current measurements. Then you have to probably need to convert it into some other form, let's say to a voltage signal. Then you might need to send this current through a resistor, and we all know about the Ohm's law. Then instead of measuring the current, you would measure the voltage. And 4 to 20 milliampere, this is not the only way that we can measure process values. There are some sensors which supports other communication protocols, for example, CAN communication or RS-232 and so on. So if, for example, this sensor is attached to some kind of electronic circuit that is responsible for sending temperature data as some form of message. Then the controller should read that message. As I said before, it could be a CAN message. Then the temperature controller or the software should running on the controller should decode that message and read the process value. The same goes with the valve. So in this case, I have assumed that we use a voltage signal to manipulate the valve, but it is not necessary that there can be other ways of doing that. As I mentioned before, with the pressure temperature sensor, it is possible to place a valve drive which can understand CAN communication. Okay, so then if that is the case, the temperature controller should send a CAN message to the valve drive, so that valve drive can decode it and act accordingly. Oftentimes, when you have to design a controller, oftentimes we need to develop a process model, which is some kind of mathematical description of the process that you are interested in. So in this case, we have one control signal, which is let's us assume that is a voltage signal, and so that is the control signal. And temperature is the one that we should control. So what controller does is that it reads the temperature using a sensor, and if it should be decoded if it is necessary. The temperature information should be decoded and compare that process value with the set point, and the controller will decide what would be the control what should be the control signal. So but how to first, how to develop a mathematical model? There are some processes which are inherently difficult to model. Some are easy. So in this case, let's say that we don't know the composition of the incoming liquid, and something complicated. The reaction kinetics are complicated, and so on and so on and so forth. So it's difficult to model the system. Let us assume that. So if that is the case, one possibility is to get a data set by exciting the system by giving a known input by known control signal. For example, let's say we can give an excitation to the system by giving a sinusoidal wave. So we has a sinusoidal wave, and maybe with varying frequency or varying amplitude. And you measure the temperature. And using those, using that data set, we can calibrate a model. And that process is called system identification. So remember that first, if you oftentimes when you want to design a controller, you need to have some kind of model. So either you can model it using equations. If it is difficult to model the system using equation, using a set of equations, then you use a data set to create a model. I can give one industrial example. Think about a cement process, and they have these rotary kilns. The reaction kinetics are so complicated that it's virtually impossible to model. So I'm talking about something like that. So once you know the model, then actually you can design a controller. And I should mention another thing. Let us assume that inflow and the outflow are maintained at constant. So we can easily do that by having, some kind of constant flow, some kind of constant flow mechanism, right? But we cannot control the temperature of the incoming liquid. So maybe in the morning it could be 20 degrees, maybe in the evening it could be 15 degrees Celsius. So we say that the temperature of the incoming liquid flow is a disturbance to the system, and it can be something which varies so slowly or sometimes quickly. But either way, it is unpredictable and it can disturb the performance of the control loop. So assume that you have to keep the temperature at 35 degrees Celsius. So that means the set point should be 35. And you let the controller to stabilize the system. Let's say after 15 minutes, the measured temperature is almost equal to the set point. But if all of a sudden the temperature of the incoming liquid drops, let's say it drops by 5 degrees, then the output temperature would drop with the input temperature. So the controller will soon react and try to compensate what the disturbance has done to the system. So a controller has two main objectives. One, the process variables should be, a controller should maintain a process variable at a desired value. And also it should reduce the influence from influences from disturbances. So here I have summarized that, summarized the control objectives. The main objective is that the actual temperature should follow the set temperature, and the controller should reject the disturbance effect. So these both are very important. Yeah. Any questions?
No, Anushka, you can continue because all are muted. So
Okay.
questions they will type on the chat box actually.
Okay. So then you will let me know.
Yeah, sure.
Okay.
So the audience, you can write any questions if you need to ask from Dr. Anushka, so that I can coordinate actually. if there is any question, you are free to type in the chat box. Or else you can raise the hand, then I can unmute if you request.
Okay. Example 2. This is something for mechanical engineers or people have worked with hydraulics. Probably some of you would might recognize what kind of valve this is. So this is a valve with a movable spool, and two of the ports are connected to the drain, and one of the ports is connected to a high pressure, some kind of high pressure source. And if you move this spool to the right, you can see that this high pressure port would be connected to the right hand side of this rod, and the left hand side would be connected to the low pressure side. So the result is the rod would move to the left, and same would happen if we move the spool to the left. So it is by using a magnet, some kind of magnetic arrangement, we can make that happen. For example, if you send a high current on the right hand side of the coil, we can have a force acting on the spool in this direction. And if you do the opposite, there would be force on this side, and so on. We can do that by using a single voltage. For example, if we supply 0 voltage, then the spool would be at its mid position or the center position. If the supply voltage is positive, then the spool would tend to move to the right, and so on. So here we have one control signal, and we can use that to control the rod position. And unlike the previous example, in this case, we can write some equations. The system is not so complicated. So assuming that the density is constant, or the liquid is incompressible, and for hydraulic application, in many cases we can assume that. So if we apply the Newton's second law to the spool, you get this equation. So it just so ms is the mass of the spool, and zs double dot is the acceleration, and f is the force generated by the magnet, and that is a function of v input voltage. And we assume that there is some kind of spring and damping force. And also we can write this equation using using the continuity equation. That yeah. So we have two equations. So in this case, we have a model. We have a dynamic model. And the model contains several parameters. Mass of the spool, and some constant, K1, K2, and so on. And some of the parameters are known, some are unknowns, or even some are known but uncertain. For example, we might approximately we can approximately calculate the mass of the spool. What we can do here is that we can get the data set as we did in example 1. We can estimate all these parameters. So this is also some form of system identification. But the point here is that either you write equations or not. If you cannot write equations, you would come up with some kind of black box model. That means you cannot write equations. You calibrate a model purely based on data. But in this case, you have some information about the system in terms of equations. But what we do here is that we only calculate the parameters. So we call that gray box modeling, because we know something, but not all. So probably you would understand what I have done here. So we have to control the rod position. So you have to measure that, and it should be fed to the position controller, and it the controller would compare that with its set point, and accordingly based on that the controller will send the voltage signal to the I think it is in. I think this is enough to have some kind of basic understanding about modeling and control of physical systems.
Doctor, there is one question from Upeka Boteju. I will read the question. There are existing process models like first order and second order. How we select such existing models if process is more complex?
If the process is complex, then you would probably get a data set and assume that the process is actually a second order system, but you don't know it is a second order system. And probably you can just excite the system with a step response, step input, and you can see what kind of response you would get. So you might get a response which resembles to a second order system. So there's no hard, there are no rules saying that, okay, this is how you do it. This is an art. Process modeling is an art. So so you have to sometimes try a lot before you come up with a good model. Yes, if it is a first order model, then probably you will see if you excite the system with a step input, then it would have a let's say a nice underdamped step response. So then you would at least know it is approximately a first order system. Does that answer your question? Or?
Yes, doctor. So we'll continue.
Yes. An early summary for what we have discussed so far. If you want to live around modeling and control the business of modeling and control, you should be good at process modeling. I have already mentioned about system identification. So there are certain things that you should learn. And there are many controllers that you can think of. You can think of PID controllers. You can think of fuzzy logic controllers, model predictive controllers, or MPC control, MPC, or some variants of these. PID is the one mostly used in the industry. So it is very important to master PID controllers. And also controllers are implemented on digital computers. So often you need to discretize. So if the controller is in continuous domain, then you have to discretize it so that you can implement that on digital computers. Okay, now we would start to go into implementations. First, we would think of something very simple. We can implement a class of simple control systems using Raspberry Pi computers and Python. This is something for hobbyists, researchers, or teachers, and so on. If someone is willing to use Raspberry Pi for industrial applications, that should be done with care, because these are not designed for heavy-duty industrial usages. I have mentioned Python here. Of course, it is free, and it's a very useful language. But you are not restricted to Python. You may use other languages like C or C++ as you want. And instead of Raspberry Pi, you could use, for an example, Arduino boards. So let us consider one of the examples that we have already looked into, controlling the temperature of this chemical reactor. So I have already mentioned that we need a temperature sensor and a valve. And we should read the data sheet of the temperature and understand how it generates, how it sends temperature information. As I said before, it could be 4 to 20 milliampere current signal or something else. And same goes to the valve. First, you should understand that. Sometimes you might have to let's say you have you already have a DAC device which doesn't support reading current signals. You can actually convert current into voltage and so on. So you should design your system first. And every software development project should start with a set of requirements. So by experience, we know that temperatures don't change. Liquid temperatures don't change so fast, so quickly. So we assume that this is a very assume that by experience we know that this is a very sluggish process, and it is enough that we calculate the control signal every 25 milliseconds. So we call it the loop rate. So that means we measure temperature every 25 milliseconds, and calculate the control signal, let's say based on a PID controller, and send the control signal to the valve. So we have a loop which calculates. We have a control loop which calculates the control signal every 25 milliseconds. And also when it goes to real-time systems, real-time industrial systems, it is very important to have some kind of fail-safe design. For an example, let's say the input flow pump drive sends some some kind of overheating within the pump. So then the software that you write should do something about it. Okay, so the having a fail-safe software design is very important. And also the operator should be able to interact with the control application using some kind of an human machine need some kind of human machine interface or very simple graphical user interface. So that can be run on your mobile, on your PC, on your tablet, and so on. So here I have given one simple implementation. The controller is run on a Raspberry Pi device. And a graphical user, you can create a graphical user interface like this. You can run that on your mobile. Let's say we run it on your mobile. So where you can set the temperature set point, and that information is transferred to the Raspberry Pi computer through wireless Ethernet communication. If the Raspberry Pi device and your mobile, if both are connected to the same local wireless network, you can write a code. You can write your software in a way that they can communicate each other very easily. So yeah. And how to implement the control application. We can implement the control application as a state machine. So that means that you operate your system step by step. For example, there's an initialization state, then the system goes in to the startup state, and from there you can go to either manual control mode or automatic control mode. So if something goes wrong during any one of those states, then the system should go to a predefined safe state, and ultimately to a shutdown state. So that would be much clearer with this diagram. When you start your control application, which runs on the Raspberry Pi computer, when you run it, it will go to the initialization state, where you do basic checks for various error conditions. You would check if the operating conditions are at desired values. For example, if you expect certain gas volume to have a minimum gas pressure before the startup, then during the initialization state, that condition should be checked. If not, it should give some kind of warning to the operator so that that gas volume should be refilled so that desired pressure is achieved. So you can see that once we start the application and go to the initial state. And if something goes wrong here, for example, some fault on a valve, some kind of error detected, because in the industry, you cannot expect that if you send a signal to a valve so that it should be opened, but there might be cases that it will never open. So you have to somehow detect those errors. And if such an error is detected, then the system would not go to the startup state. It would go to some kind of some other state where we will shut down the system, for an example. And if everything goes smoothly during the initialization state, the system will go to the startup state. And we know that every system, generally, every system has some kind of startup stage. We cannot just start to run the controller on a dynamic system. That will not work. So first, you should have a startup state, and if that is done, then operator can decide whether he wants to go to the manual state or the automatic state. So that action could be just clicking a button on the HMI or the GUI. So either from the startup state, either the system would go to the manual state or the automatic state, and it is possible that the system would go from manual state to auto and auto state to manual, again based on the operators. Yeah, and you can see that there is a safe state, which is a predefined state that's that the system would arrive at if anything goes wrong within any of these states. You can see that if something goes wrong with the startup state, it will go to the safe state, and so on. So here, for example, you would turn off some valve, turn off some pumps, close or open gas, closing and opening valves, and so on. So safe state would help us to shut down the system with limited damages to the system and possibly to the workers around the system. And let's see how to implement this state diagram using Python. I have written a pseudocode using Python. This is nowhere near to be a good program, but it contains most of the elements that you can start from here and start to add more and more code to it, and it will come to a good program. You are not restricted to Python. If you know C or C++, I would strongly recommend to use those languages. But in this case, the control loop runs every 25 milliseconds. So Raspberry Pi probably can handle it, because that's 25 milliseconds is quite a big sampling time. But if you want to have sampling times much smaller than 25 milliseconds, then probably you should think about using C or C++. And Mahawat should notify me if I am taking too much time, or.
No, I think we can continue, Dr.
Okay. I have mentioned already that the system would start with with the state initialize. So I have defined a variable called state and assign it to a string, which is called initialize. And I start a while loop. And the first thing we do, we just measure the temperature. So you should write the code to read the temperature. And then we start the state machine and we check the current state. For example, if the state is initialized, which is the case when we start the system for the first time. And we do some basic checks, which I have explained before. And if any error detected, then we change the variable state into shutdown. So which means when the loop starts next time, the state is equal to shutdown. So only shutdown state, the code belongs to the shutdown state. Only that will be executed. And if the state is manual or auto, then accordingly the controller will send the control signal to the actuator. And at the end, we have the safe state. If just in case the safe state is activated, so system would go to a predefined safe state. For example, we can do some turning off of certain pumps and motors and so on, which I have explained already. If you want to write a program using C or C++ or something else, this is the structure, kind of the structure that you should follow. And if you don't have any prior experience in programming, maybe you can just have a look at this once you have done some, once you have some basic understanding in programming. This is not, it looks complicated, but actually it is not so hard. And how to create the GUI application or the HMI application. For me, I always start with Python if I have to create an HMI, because that's, you wouldn't expect, you know, HMI is a very lightweight application. Often it's a very lightweight application, but the control application is, it is quite heavy. So that's why I strongly recommended that you would consider C or C++, because those languages are quite efficient and fast, much faster than Python. But for an HMI, Python would be more than enough. But if you don't want to use Python, you can use LabVIEW, C, C++, or whatever favorite language that you can think of. So here I have created an HMI using Python. You can see that I can connect this HMI application to the control application if we know the IP address of the Raspberry Pi computer. Okay, so then you can actually, once you have established the communication, you can send information to the control application, which runs on the Raspberry Pi device. As a summary to what we have discussed so far, we have used Raspberry Pi computers to run a control application. The latest Raspberry Pi version is Raspberry Pi 4, and I just converted the cost that you know, if I had to buy that from Norway, then I would spend a certain amount of Norwegian kroners. Then I converted that to Sri Lankan rupees. Then it was I got the number 23,000 rupees. And if you go for the previous version, which is still good enough, that would cost around 11,000 rupees. But the good thing about Raspberry Pi computers is that this is something for students, educators, and researchers, and so on. Let's say you are doing a PhD and you have a small lab setup or a pilot scale experimental setup. You don't need to buy or you don't need to struggle that you cannot, if you don't have money to buy some kind of solution based on PLCs or so you can create your own control system or data acquisition system using Raspberry Pi. Of course, if it is good enough for your application, then this is a good cheap solution, because you can program a Raspberry Pi computer by yourself. So it's so there are some that the reason why I mentioned Raspberry Pi computer about Raspberry Pi computers in the first place, that it can be used in academia and research. And of course, Python is free and easy to learn, and is one of the it has become one of the most popular programming languages among students, teachers, and researchers. now we are done with Raspberry Pi computers. So we go a little further. We would consider something much more complicated than that. Microcontrollers. So how to use microcontrollers in automation? Microcontroller is loosely speaking, it is a tiny computer. Here I have shown a 32-bit microcontroller. The manufacturer is Microchip. A microcontroller contains a microprocessor and some kind of memory, and most importantly, peripherals. So the peripherals are the ones that we use to interact with the rest of the world. You have a microcontroller, then you use the peripherals to interact with sensors and so on. So you can see here that this microcontroller has so many pins, and some pins can be configured as digital input-output pins. Some can be configured as analog input. Some pins can be used in serial communication or UART communication, some in SPI communication, and so on. So these devices give you more flexibility and more freedom. You can do very basic tasks like lighting an LED to controlling a vehicle. So these are very powerful piece of equipments, components. So let's look at the internals of this particular microcontroller, PIC32MX360F512L. So if you look at the internals, you can see that there are about 7 digital input-output ports. For example, one of them can be used to light an LED or turn on a motor by sending a digital high-low pulse, and so on. And it also supports USB communication, direct memory access, which we will not discuss because it's a bit complicated and hard to explain. And it has a built-in analog to digital converter. That means you can connect an analog signal to this microcontroller and read it and it has a 10-bit resolution. If you want higher resolution, maybe you can buy a separate chip or separate analog to digital converter with higher resolution, let's say 16 bit resolution, and get the data from that external chip through some kind of communication protocol, let's say I2 squared. So you can see that you can do, you get more freedom if you start to use microcontrollers. But as I said before, these devices are not easy to work with due to a couple of reasons, which I explain in the next slide. How to program a microcontroller. So often we use C, the C programming language, to program microcontrollers. Of course, we can use C++ or assembly, but to the best of my knowledge, C is the most popular. So mastering C or C++ is not so easy as Python. But when it goes to microcontrollers, you have limited options. You must either use C or C++. If you are good at assembly, you can use assembly, but it's a very difficult language to handle. So for me, it's mostly C, or almost exclusively C language. So the challenge is that how to master the C language. So let's say if you can learn Python language within 6 months. To master C language, you would take maybe several years. So that is the challenge here. So you have to use either C or C++, which are not easy to handle. Well, they are not impossible to understand, but it will take some time. You would need some experience before you come to a level that you would confidently start to produce industrial grade software. How to program? Well, you can use if you consider microchip products. That company provides an IDE, MPLabX. You can use that to develop your applications, and you can download or flash those applications into the flash memory of the microcontroller using an external device. We call it a programmer. So that's it. So the one, if you are ready to take a challenge and learn C, and then you will enjoy. I'm pretty sure that you will start to appreciate these powerful small devices. A summary: if you want to work with microcontrollers, you need to be good at embedded C and C++. At least these two, at least one of these languages. And these devices are ideal if one wants to start his own business, because you can develop your own software. So it will be proprietary for you and for your business, and you just need to buy microcontrollers. You would not buy ready-made products. You buy microcontrollers and you program them by yourself, and you sell your product. And yeah, and Microchip is not the only manufacturer. There are many others. For example, yeah, there are many other vendors. You can Google, and you probably will get a long list. Now we will do something a little bigger than what we have talked about. So let's see how to control relatively related to a larger system. Say a system which involves 200 sensors, or let's say 150 sensors, and some actuators, of course. In the beginning, I emphasized that I'm a chemical engineer, so I focused my talk mostly on chemical and process engineers. So I need something. I need something that chemical engineers can implement. So already I have pushed my limit a little bit. So I have gone to the world of software development and embedded systems. But we cannot do the things that electronic engineers should do. But software development, I think we don't need a degree in programming, degree in computer science to become a programmer. I think anyone can be trained to be a programmer, but I'm not sure about electronics. So if you think about something that chemical engineers, a group of chemical engineers can, a system which can be used by a group of exclusively by chemical engineers to work with. So I have found such a system, and I'm pretty sure that this can be used. This may be useful for electronic engineers if they haven't heard about this before. Before going to that, I have a question. A general purpose computer, say running on Windows, may not be ideal for running a real-time control system. Can anyone say why?
You can unmute and speak actually. Anyone can unmute and speak.
Delay. There is a lot of delay. Oh, can you hear me?
Yes, we can hear you.
There is a lot of delay when we use Windows type operating systems, computers. So that causes instability problems for the control systems.
Dr. Anushka, are you there?
Dr. Anushka is muted.
Can you hear me now?
Yes, sir.
Hello?
Yes, doctor.
Yeah.
Yes, we can hear.
Yeah, I kind of agree with what you said. If you are running a control system or control application on a general purpose computer, you know, if you have heard about a schedule, one of the components of you know, the scheduler will allocate resources to different processes running in parallel. So there's no guarantee that your control application would be given the desired priority. So if you want to run a control loop every 5 milliseconds, then the control, then the operating system must run that process every 5 milliseconds. But we cannot expect that from a general purpose computer. So we need to have some kind of real-time operating system. One possibility is to use real-time Linux operating system. So which I have used extensively during last 4 years, and I think this is one of the best real-time operating systems I have ever used. As I said before, I'm looking for something for chemical engineers, and we need something compact, rugged. We need something with acceptable performance, and it should survive. It should be able to survive. That system that we are going to use should survive for some, operating conditions matters, and we need some kind of industrial grade embedded controller, and modularity, extensibility, customization. Yeah, there's so many requirements, and those are the hardware requirements. There are software requirements. We should think about the cost, reliability, security, determinism, easy to work with, because we are chemical engineers. So we need something simple, and productivity, and the support for C and C++ application development. So this is what I have found, which satisfy all the needs. That is called the compact Rio architecture. This one is designed for industry, and it is from National Instruments. It's a well-known big firm company, and there are three main components: a computer running on a real-time Linux OS, and a FPGA chip, and of course industrial I/O modules. So those modules can be analog modules, digital I/O modules, and many other modules which supports industrial communication. For example, CAN communication, PruPinet, PruPBus, RS-232, and so on. And the challenge here is that we need to program 3 targets or 3 devices. One, we have to program the HMI, which is relatively easy. And we have to run our control application on this computer, which runs on a real-time operating system. And we have to program this FPGA chip. So this FPGA chip is the one that we use. It acts as a middleman between the computer and the I/O modules. As I said before, we run the control application on this computer, and on FPGA level, we don't have a thing called operating system running on the FPGA chip. It's just a standalone application. We have to write the program and just burn it to the chip. So there's no operating system. So that means there wouldn't be any software failures. So this device gives us the reliability. So it will almost never fail. So this is the bound that this is the upper bound that upper bound of the reliability. So as long as it is there, so we can have some kind of safety in our system. So we implement a basic safety logic on FPGA level. For example, if there's a software failure, if the control system crashes, control system application crashes, then the FPGA can restart the application running on the computer. So how to do that? It is possible to run a watchdog loop, on FPGA level, so that if the control application fails to pet the watchdog loop, then FPGA application would know there's a crash on this computer. So the FPGA will restart the computer. And the good thing about this architecture is that FPGA application can still run. So that means the safety logic can be implemented on FPGA level. And if you want to extend, if you want to, as I said, this is a computer, even though it is running on a real-time operating system, it is just a regular computer. So it supports standard communication protocols like RS-232, PYTHO, Ethernet, and so on. So you can connect, not only you can connect sensors to the system through I/O modules, you can also connect sensors through directly to the computer. And how to program these 3 devices or targets. So we have already discussed that an HMI can be developed using Python or LabVIEW or LabWindows. That's the C version and CC version of LabVIEW, or C# or just whatever you like. The application running on the computer can be programmed using LabVIEW or entirely using C and C++ or C++, or some kind of combination of those two. On FPGA level, you know, for a small scale system, it is very difficult to hire someone develop FPGA applications using some kind of hardware description language like VDH, VHD. Yeah. So for me, almost exclusively, I tend to use LabVIEW FPGA programming facility to program the FPGA chip. I would never go and I will never use a lower level language to do that, because already, I mean, to program an HMI and the real-time application, that would take a long time. And probably if you are programming in C for 6 months, and then if you switch back to FPGA programming, probably you would have forgotten what you did 6 months before. So for me, I always use LabVIEW FPGA programming facility to program FPGA chips. So that would give me a higher productivity, and it is something that chemical engineers or someone would chemical engineer would handle. Yes, and one final comment. Let's say you have a system with 100 sensors and 50 actuators. Then how would you make a small system sensors? So probably you can buy sensors and actuators which are supported by CAN communication, the CAN protocol. Then you can connect all those sensors to the CAN through a CAN I/O module, so that you can interact with all the sensors. Yes, and I think that's the end, and I have covered almost what I have to cover. And yes, and if you have any questions, we can take it from here now.
Dr. Anushka, we have a number of questions in the chat box, so I will go one by one.
Yes.
I think already we have answered for the first question. Okay. So second question is from Jagat. I will read the question. It says, so you have got quotation for disturbances as well. Can we do it practically?
Can you please repeat the question?
I saw you have got quotations for disturbances as well. Can we do it practically? Jagat, if you are there, can you please elaborate? Your mic, yes. You can unmute.
Sorry about the auto correction. It has to be equation, the mathematical modeling.
Okay. So
equation.
So you are asking if you can develop a model for the disturbance effect?
Yeah. Is it practical? Can we do that actually?
Well, for some, yes. For example, in that case, if it is possible to excite, if you can somehow change the temperature or measure that using a sensor, then you have that data, right? So then one thing you can do is that you can maintain the valve position at a constant value, and you then you can actually see the connection between the disturbance, the connection between the disturbance and the temperature in the reactor. So then you can actually make a model between only those two. But if you cannot do any experiment, then there are other ways of doing that. We can define a model with some assumed structure for the disturbance model, and we can do some trial and error. Then you can come up with some kind of stochastic model which explains the disturbance effect. Yes.
Yes, doctor. I will move to second question. So it is from Rakita. And the question is, how about the SCADA controller? Brief introduction is required. I think this is regarding first few slides.
Okay. So can you explain that question a little more? Or is it?
Rakita, are you there? You can unmute and discuss.
Yes.
Are you talking about this one or?
No. Actually, I'm talking about additional questions. That is, now it is trend to use SCADA controller for almost all the process control. So that's why I'm asking that whether you can describe and integrate this system with SCADA system, and we have any comparison between these two systems. That's why I just asked the question.
So are you thinking about this compact Rio system I mentioned, or?
No, I think he's asking whether we can connect these systems with the SCADA controllers.
Yes.
Since it is already used in the industry. Yes, any kind of IO module that you can incorporate into your software. But remember that I am talking about small or medium scale systems that maybe 5-6 engineers can handle with. So if you go over that, if you think about bigger systems, then I think there are already ready-made. There are service providers that they can provide you with the complete system, so I focused exclusively on very small systems. So we.
Anushka, please unmute yourself. I just muted, I think.
Yeah. Yeah, I think if you have money and if you want a ready-made solution, then I think why not? It should be done. But if there is a small-scale system that it cannot spend that amount of money, or it cannot hire external consultants and so on, then yeah, my objective is to show something that 3, 4, 5 engineers can get together and just build things from scratch, almost from scratch, and start to sell or commercialize. Yeah, there's a mark. I think there's a market for that. Yeah.
Doctor, next question is from Jagat. is asking how to select between PID, PD, and predictive fuzzy actions.
PID, PD, and
PD and predictive fuzzy actions.
well, you know, it is impossible to. You just named 3, and if I ask why only those 3, I think it should not be like that. It should be. If you ask me to compare, then it's a different story. But if you cannot start with predefined control algorithm, there's no universal solution for every control problem. So if it doesn't answer your question, maybe you can please you can elaborate a little more.
What I meant was like, now you will write the program and all, and then sometimes you will also analyze the process. Now, I just took those control algorithm as an example. I know there are a lot more than that.
Yes.
So based on your experience, sorry, I couldn't add that word. Based on your experience, once you are given a process, a massive process with all logics and all the sensors and actuators, on what ground you choose? Should I go with P or PID, or maybe sometimes very simple control like on-off controller, or very complex control like predictive controllers, or maybe something related artificial intelligence also?
Yeah,
I'm just asking your experience.
Yeah, I think I would start with you know, we can always get historical data, you know. So I will try to understand as much as try to understand the process as much as possible, and I would look for a data set that would lead me to some kind of you know, to understanding, like if your best friend is to analyze the process data, and then I would try to calibrate the model and see if the system behave. Let's say if there's a second order system, and I would get a data set, and probably I would see by looking at the responses, or even using some kind of system identification technique, I would know that, okay, this process is somewhat behave like a second order system. So there's no ready-made. So as I said before, there are no ready-made solutions. And according to my experience, even to tune a very basic PI controller for an industrial application, I mean, even that would be quite challenging. So we have to take them case by case. And I would talk to operators a lot, and of course for the process engineers. Yeah, and
The next question is from Mushtaq Ismail. So he's asking about better way to develop the GUI with ease, graphical user interface, to develop a GUI with easily, actually. Asking for a better way.
The better way is let's say you have to make a GUI within 2 weeks. So the customer is waiting on the other side, and you have only 2 weeks. And I would start with Python, and because that's the easiest to finish. That's the best language for me to build something very quickly. If you want to make a GUI which needs more performance, maybe then I would use some some other languages which would give the performance. So again, there's no one way. It's you should it depends on the task that you have, but often for me the first choice is Python, because it's much easier to handle. Yeah.
Okay. Next question is from Upeka. How do we find loop rate? Don't you need the time constant value of the process to find it?
Yes, that is correct. We need that. If you have you know, that's why I told in the beginning, can you see my video, or should I okay.
Yes, we can see. We can see.
We can see.
If I mentioned that the process is sluggish, that means it's slow. That means things happen very slowly. So if you know the time constant, let's say time constant is 2 seconds, then you can have like 10%, less than 10% of that as the loop rate, as a rule of thumb. Yeah. If you can go, you can go much lower than that, but then you should be, you should make sure that you can go, the processor can handle it. No. So if you are using Python to run your control application, then if you want to run with the loop rate 1 millisecond, and you have a lot of calculations going on, then I would not go for Python. Then I would go for C or something else.
So I have another question.
Yes.
Within that loop rate, we have to give the control command to the actuators. No? The one loop rate, one actuator command. After the another loop rate, another actuator command. Is that the idea of that?
Yes. Yes. Yes, that is correct.
Right. Okay. Thank you.
So next question is from Jayasurya. What are the reliability measures we should consider? His mean the hardware like RPI and its operating system. What are the reliability measures we should consider?
First of all, I would never use RPI, Raspberry Pi, for industrial application. That's number one. Number two, it's a general purpose computer and running on a general purpose operating system. So I will not use it for, I will not, it's not reliable. So there's no guaranteed, you know, if you want to run a control application, if you want to calculate the control signal every 5 milliseconds, then there's no guarantee that it will happen. Actually, we call it, we cannot achieve the determinism if you use a general purpose computer. So because there would be a jitter. So if it is, if you want 5 milliseconds, if you want something to happen every 5 milliseconds, then it will happen. You know, there things happen around that, but not exactly on that. So general purpose operating systems would violate the real-time requirements. So that's another thing. If you want to run a real-time application, you must have a real-time operating system, because then you can actually prioritize the control loop so that there will be guaranteed, you know, it will run exactly when we want it. So so this is not for industrial applications, but I clearly mentioned that this can be used these things can be used in research, because if you are running a loop, if the loop rate is 25 milliseconds, then I think even though this is general purpose computer, it will be okay, because we don't need the it will. But the problem comes if you want to have lower. And at the end, I pointed out that there's one possible architecture that you can use, that is the compact Rio architecture. Then you can, but that's rather expensive. You can buy that and use the real. Then you get the chance to use the real-time operating system. Or else you can install a real-time Linux, and you can somehow impose this real-time Linux patch on that, so that you can make a Linux operating system into a real-time operating system. Yes. Yes. I hope that answered your question.
Yeah. There's another question from Jagat. Is asking about the sampling rate. Can you comment on sampling rate, A to D resolution as well?
I didn't understand the second one. What is A to B resolution?
A to D resolution.
Okay. Sampling rate is as it implies, you have to take samples every certain milliseconds, for example, right? The resolution is, let's say you want to read an analog sensor which gives values between 0 and 5 volts, meaning the lowest is 0 volts, the maximum is 5 volts. And digital computers, microcontroller will never read an analog value. It will read analog values as a digital. Yeah. So let's say it's a 10-bit resolution. Then actually you can start with you will have how many numbers you can represent with 10 bits. That's equal to 2 to the power 10 minus 1. Sorry, 2 to the power 10. So that you can measure that many levels, right? So let's say the analog sensor gives 0. So that is equal to binary 0, 0, 0, and 10 zeros. And let's say if you measure the maximum voltage 5 volts, then that would represent that would be equal to 1, 1, 1, 1, 1, 10 ones. So all the values in between would be represented by the binary values in between 10 zeros and 10 ones. So now you see that after 0, 0, 0, after 10 zeros, the immediate next binary number is 0, 0, 0, 0, and the last one is 1. You see? So you have finite steps, finite set of values that you can represent using yeah. So so if you want to have better resolution, then you have to increase number of bits. Then you have many divisions. So you can the more bits you have, then you can represent an analog signal as much closer to the actual analog signal. Yeah, that's what it means.
Yes, doctor. The next question is from Kasun. So sorry.
Yeah, sorry for disturbance. Thank you very much for the explanation. But what I really meant was, like, when it comes to the normal process controlling, what are the ranges that you are going in terms of this sampling rate and A to D resolution? That's also I wanted to know.
Yeah, but it depends on what you need. I think if you want to run a loop, control loop every 1 millisecond, then no, every milliseconds, not that. If you want, okay, I can give an example. Let's say you are measuring a signal from 0 to 10 volts, right? Then if you use 10-bit resolution, now you can understand the error will be high, right? Because you are measuring from 0 volts to 10 volts and 10-bit resolution. And can you compare that with something like you have the same resolution, but you measure between 5 and 0 volts. If you are measuring something between 0 and 5, then 10-bit resolution will give less error than 0 and 10, right? Agree? So then I would use high resolution if I want to measure large range. So it depends on the accuracy you want. If you want high accuracy, if you want to measure something with high accuracy, then you must have higher bit rates. Resolution.
Yes. Hi, Dr. Shall I move to the next question?
Yes.
Yeah, the next question is from Kasum. So he's asking why we can't use small low-cost PLC with embedded HMI to implement the control.
Yes, you can do that, but where would you implement the real-time control application? Or on the PLC?
Yes, should be.
Okay, but you know, sometimes it is enough to implement a PID. It is very easy to implement a PID because the algorithm is very simple. Once you have tuned, it is just a matter of you know, if you have tuned the PID controller, then you know all the controller gains, proportional gain, integral constant, and so on. And then you discretize it, and then you just plug it. That's much easy. Just one line. You calculate the control error, then you just, yeah, it's much easier to implement. But if you want to implement an advanced algorithm, advanced control algorithm, then you need a powerful processing element, like a computer running on a real-time operating system, so that you can implement that algorithm within that processor, within that computer. So if you are thinking about small and medium scale systems, that's why I kind of, this is not for all small and medium scale systems, but a class of small and medium scale systems. Then you should identify what solution is the best. But I emphasize that for some control algorithms, you need a stronger processing element or something that is powerful enough to implement an advanced algorithm, like a model predictive controller. So of course you can use a PLC that would interact with sensors and so on, but still we need a process, some kind of processor that would implement advanced algorithms. So I have implemented the MPC model predictive controllers on yeah.
Yeah, doctor.
Yes.
So next question is from Dimutu. So he's asking whether we can use open source software like CFD for CFD modeling.
No, not for, well, I cannot say no, but CFD like software are mostly used for simulations, right?
Yes.
And there's a clear difference between modeling for control and modeling for simulations. And oftentimes, if you are doing a CFD simulation, let's say Fluent software, so that will run, that will solve a bunch of partial differential equations, right? So if you think about a control loop which runs on which runs every 5 milliseconds or even 1 second, every 1 second, it is necessary that the model is simple and good enough. We don't need the fancy complicated models like CFD models. That we cannot use them. So the CFD modeling has, it's very useful, but we mostly use them for simulations, not for control applications. And I would, that would be the last thing I would ever consider as a control engineer to use for modeling purposes. So remember that you need to develop the simplest possible model which captures the main dynamics of the system. So simpler the better. And if it is a third order system, I think I would be happy to see a system, let's say a maximum 4th or 5th order, not more than that. Yeah.
Okay, doctor. I think that clarifies. So next question is from Supun. So he's asking about a scratch method for programming microcontrollers.
You mean?
Is there any scratch method? Maybe some easy way to program microcontrollers?
Well, I think if you want to be very serious about microcontroller programming, then you must stay around C, C++, assembly, and maybe basic. So I think most of the time it is C. And I know there's a possibility that you can use Python to program microcontrollers, because there is a version of Python called MicroPython, which can be used to program a set of microcontrollers, but not all. It's still being developed. I have done some program. I have programmed some microcontrollers, several microcontrollers using Python. I think I would not like that, but it has become quite popular among the kids, that people, especially in the UK, they have started a big project that they use Python to, like 7th graders. In the UK, they have introduced microcontroller programming using Python. As I remember, they start from 7th grade. Yeah, but for industrial applications, I don't think we should go for anything other than C, C++. If someone is extremely smart, maybe assembly and basic. So yeah.
Yeah, doctor. So next question is about the cost of RIO comparatively with Raspberry Pi and cost of IDE. whether they are available on free basis or we need to purchase.
What was the first one? RI?
RIO, Rio,
Okay.
Rio and Raspberry Pi.
Yeah, okay. Raspberry Pi. Maybe I can show you that. It would be interesting to see that. I can share my. Can I? Am I allowed? Okay, I'm allowed to share. Can you see the see my camera?
Yes.
Okay, I can show you a couple of. This is a Raspberry Pi. I bought this for about 400 kronas. So if I multiply this by 20, then it's about 10,000. I think it's this one. You can buy it for 10,000. But I don't know if you buy it from India. I think you can buy it from India. Right? About 10,000 rupees. So yeah, and you just need to do something with a simple SD card, and you install your operating system on this and just plug it in and boot it. Yes, but this is very good if someone is doing a PhD or something and then want to automate, to make some. And this is a Arduino board, and it comes with a microcontroller. So you can remove it, and if you want to program, you can just remove it and program, or just use the Arduino IDE to program. And I will show you a microcontroller if you haven't seen one from before. See, this is a microcontroller, a 32-bit micro, and you can build quite an advanced control system using this. It's much cheaper. So you just need you need to get some help from an electronic engineer and to do the PCB design, and and if you want to buy serial board, that is quite expensive. But if you want to start a business, then I think you have to invest some money on it. But you have to be very careful before buying if that is something you really need. It can be very expensive. But if you want to start a business, then I think this is a device that I normally use to program a microcontroller. So probably you would need to buy one. If you want to learn programming, you want to buy one, and you just do something like that. So there's a microcontroller, and you want to program it. You connect this one to the microcontroller and connect this device to your computer and program it, and just download, just flash it. And you asked me about the software. For non-commercial activities, the microchip provides a free IDE, so it's free. You can use it for, if you want to learn, you just use it for free. But if you want to use them in production, you have to buy. But I don't think it would be that expensive as compared to the possible income that you would get.
Yeah, doctor. Shall I move to the next question?
Yes.
Yeah, next question is from Kasum. What is the tool are you using to identify the model? Is it MATLAB Simulink System Identification Toolbox?
Yes, exactly that. Yes.
Exactly. Okay.
Yes.
So we'll move to the next question and the last question from Dimutu. What is the most popular controlling software for large scale or medium scale control models? Most popular controlling software.
What do you mean by controlling software? Is it?
Not sure. I don't know whether Dimutu is here.
You mean you mean the software that is used to develop the control application?
Yeah, Dimutu is here. You can unmute and elaborate actually. Okay, looks like he's not responding. So I don't know, can't see this. So I think we have come to the end of our presentation. Doctor, do you want to add anything on this?
No, I think I have told almost everything I wanted to say.
Okay, doctor. So shall I invite Engineer Tisalianage to have some words about today's session and how it helps to the chemical engineering in Sri Lanka?
Yes.
Yeah, thank you very much, Dr. Anushka Pereira. It was actually a very useful session and very informative, and it's very, I would say, to some extent, it was academic. And though I'm not into this programming, I little grasp about, now you said about how Raspberry Pi computer can be used for certain applications for small scale controllers using Python, right?
Yes.
And then you move on to microcontrollers and using C and C++ and PIC assembly.
Yes.
Correct?
Yes.
Yeah, I slightly graphed those things, right? Then I noted down actually. Then you went on to medium scale systems using real-time operating system like Linux-based system for medium scale, right?
Yes.
Then you move on to tell about GUI development with using Python, right? I think those areas actually you explained very well. I think there are some engineers apart from chemical engineers, there may be mechanical engineers and so on. So I think it may be a very useful session. You explain how you can develop a business like 3-4 engineers can get together and develop a small system for small chemical or process industries and so on. All in all, it was a very useful session for chemical engineers as well as I think maybe for mechanical engineers as well. And thank you very much, Dr. Anushka Pereira, on behalf of Chemical Engineers Sectional Committee of IESL for, giving this light, giving some light into this area. This is the first time I think Chemical Engineers Sectional Committee had this type of session. So thank you very much once again, Dr. Anushka Pereira. Thank you.
And I should thank giving me this opportunity to give this presentation. I think this is something that sort of hidden that I think we should start to motivate at least some graduates to move towards process control. And yeah, so yeah, that was my main motivation when we were planning with Mahavat and Shamila that we had to motivate this kind of things within the community. So, and thank you very much for giving me the opportunity.
Yeah, I think we can wind up for the today's session. So again, thank you very much, Dr. Anushka. And actually, it was a very good session actually. So I think we can wind up the session. Thank you very much. Good night and stay safe.
Yeah, good night. Thank you.
Good night.